Hello, I'm going to do a problem for you here. This is 2.8, number 3. This one is a little bit annoying. I thought I would write this one out for you because it's a little odd. No, not really. But so we have this differential equation, and we're trying to find the eigenvalues, lambda, the positive eigenvalues, and the eigenfunctions. But we have these conditions here. We don't know the, oh shoot, sorry, let me clean that up. So we know that, we know the value at minus pi of the function, and we know that it's the same as the value at pi, and we know it's 0. Okay, so I will dispense with the case when lambda is equal to 0. That's similar to that you'll find in the book, that we don't get any non-trivial solutions. But let's look at the case when lambda is actually bigger than 0. Okay, so in this case, we assume that lambda is equal to alpha squared, and here we'll take alpha greater than 0. Okay, so this situation then leads to a general solution, as is illustrated in the book. We get our general solution that y of x will be some constant times the cosine alpha x plus some other constant b times the sine x, and our job is to find the eigenvalues lambda and the corresponding eigenfunctions for that eigenvalue. So what we've realized is we write down our system of equations, which is given by our initial conditions here, and let me just do this down here. So the first thing we get is that 0 is equal to, well, when I plug in, let's see, minus pi, then I get a cosine minus alpha pi plus b sine minus alpha pi. And if I plug in the other condition, well, the one that y at pi is 0, then I get another equation that I need 0 to be equal to, well, the same thing, except I evaluate at pi. Crush. B, I'll clean that up, sine of alpha pi. Okay, so often with in these situations, we need to use some properties of the trigonometric functions we're dealing with. So here, what we see is that, in fact, this equation, which I'll call equation E1, and then I have equation E2. So we know that the cosine of minus alpha pi is the same as the cosine of alpha pi. We know the sine of minus alpha pi is equal to minus the sine of alpha pi. So we can use the even and odd nature of these functions to change these. I can basically erase this minus sign and it's out front. Okay, and then I would need to, in fact, if I erase this minus sign, I must introduce a minus sign here. Right here. Okay, the nice thing about this situation is that we can now try to eliminate our A and our B. For example, if I take what I now call E1 plus E2, This would give me, let's see, what does that do? That eliminates the b's, but it gives me the equation 0 is equal to 2a times the cosine of alpha pi. So, okay. So this situation, right? Well, let's write down our other equation that we could get from this. If I take let's see, E2, let's say, minus E1, then I get the equation 0 is 2 times b times the sine of alpha pi. Okay, so we can get some nice eigenvalues if we make some assumptions. Under the assumption that, let's just assume that a, in this case, is in fact not 0. Okay? All right. Well, this leads to the following equation, that if a is not 0, then we would need 0 to be equal to the cosine of alpha pi, and here's where we get some information. So that means that alpha pi, well, let's see, we have to ask ourselves when the cosine is 0, right? So that's 0 at pi over 2, 3 pi over 2, etc. And in general, we get 2n plus 1 times pi over 2. So in this situation, when a is not 0, we get eigenvalue, well, we get alpha, not the eigenvalue, would be 1/2, 3/2, dividing through by pi, to 2n plus 1 halves. And now we know that in fact our lambda is this alpha squared, so we get our eigenvalues, and I'll write it this way, that our 2n plus first, okay, eigenvalue we can now calculate as, by squaring everything, it's just going to be 2n plus 1 squared divided by 4. Now, seeing where these come from, in the case when a is not 0, we can then take our eigenfunction in these equations. If I set b equal to 0, I can take my eigenfunction to be given by what? Where's my general solution? Here we are. So our general solution is that I'm going to take a equals 1, and then I get the cosine of alpha x. So then our nth eigenfunction, well, not nth, but our 2n plus first one, is going to be the cosine, right? So it's the cosine of 2n plus 1 divided by 2x. Okay, so there's our odd eigenvalues and eigenfunctions. To find the even ones, we look at the other equation, in that we will take, in this case, we're going to take, well, a equal to 0, and we'll take b, say, equal to 1, or 1/2, or whatever we like. But we arrive at the conclusion that we need to find out when the sine of alpha times pi is 0. So when the sine of alpha pi equals 0, okay, that happens when alpha times pi is equal to, and I'm going to write this in a very strange way. I'm going to write this as, see, I want to get some similar form to my solutions. Okay, so watch what I'm going to do here. I'm going to write this as, let's see, well, 2 times pi divided by 2. That's a weird way of writing pi. Then the next time that occurs is at, well, let's see, 2 pi, really, right? So I'm going to write that as, well, here, let me just write it this way. Forget this. Let's just write this as 2 pi, 3 pi. So at integer multiples of pi, I get that the sign is 0, and in particular it'd be n pi. Okay? But I want to rewrite this in a different way. I just want to write that that's the same as saying when this is equal to, and here we go. Oh, so I'm going to write 2 pi over 2, 4 pi over 2. I'm really 6 pi over 2. So I'm really just multiplying the numerator and denominator by 2. So I get 2n pi over 2. The reason I did that is because now I know that in this situation I have my alpha equaling the following. Well, it's 2 over 2, 4 over 2, and in general it's 2n over 2. Okay? And the reason I did that is just because I wanted it to look nice. So then lambda, in this case, the square of alpha, is going to be, well, 2 squared over 4. And, oops, sorry. It's going to be 4 squared over 4. And in general, we get 2n squared over 4. So in this case, when we choose for the system, a solution of the system of equations for, if we choose A to be 0 and B to be non-zero, we get the eigenvalues. Here we go. Lambda n, actually 2n, in other words, the even eigenvalues, are given by 2n squared divided by 4, very unusual way of writing it. And then we get our eigenfunctions, y sub 2n, we can choose to be the following. Are we with the sign now? Yes, we're with the sign. Yes, so we get the, yes, the sine of 2n over 4x. Okay, so there we found our eigenvalues and our eigenfunctions for this differential equation right here under the assumptions of our endpoint conditions. So I hope this helped clarify it, or at least illustrate how sometimes you have to look more deeply into the system of equations that arises as a result of this. So thank you very much. Bye-bye.